Hello students, today we are going to do the next part of the chapter series of the lecture series. As you all are knowing that we are doing chapter number 9, ray optics. In the previous lecture we studied about lens maker's formula and its application. Today we'll study about image formation by convex lens, image formation by concave lens, thin lens formula, linear magnification, and power of a lens. All these topics you have studied in class 10th also. But in class 10th, no derivation of formula was there. In this video lecture, we'll prove the thin lens formula. But the image formation by convex lens and image formation by concave lens, linear magnification and power you have already done in class 10th. So we'll try to remember the things. We'll try to understand the things more deeply as you have studied in class 10th. So let us start the lecture. The first thing we study about image formation by convex lens. So for image formation, as we have done in the case of mirrors also, first of all we'll take some important rays. The rays which we select, those rays are actually, we know the path of those rays after getting refraction. So let us see what are the rays. The first ray, as you can see in the ray diagram, it is falling on the lens parallel to the principal axis after getting refracted from the lens. As the definition is, the lens passes through the principal focus of the other side of the lens. Second ray is, when a ray passes through the first principal focus and falls on the lens, then what happens after the refraction? The ray becomes parallel to the principal axis. These two definitions we have done in the last lecture only. The next one is passing through the optical center. When a ray passes through the optical center, what happens? Ray does not deviate from its path and it goes on its original path. So these are the important rays. Once again, if you try to understand, if a ray falls parallel to the principal axis on the lens, then it passes through the second principal focus. When a ray passes through the first principal focus, falls on the lens, then after refraction, it will go parallel to the principal axis. Third ray is, when a ray falls on lens through the optical center, then what happens? It passes undeviated. With the help of these three rays, we are going to understand the image formation by convex lens for different position of object. Let us start. The first position of the object is at infinity. If an object is at infinity, the ray from the infinity which comes to the lens are parallel to each other. Here we have taken an object which is extended above the principal axis as well as below the principal axis. Then what happens? All the rays coming parallel to the principal axis, and then after getting refracted from the lens, they falls on the second principal focus. Hence we get a point size image on the second principal focus. This image is point sized, it is real, and here you cannot see, but if the object at infinity is extended only above the principal axis, then image will be inverted also. So the characteristics of the image in this case will be position of the image at focus, size of the image point size, nature of the image real. Now second position, beyond 2f. As you can see in the ray diagram, when the object is at beyond 2f, then one ray passes parallel to the principal axis, is passed through the focus, and other ray passes through the optical center undeviated. These two rays intersect at this point, so we are going to have an image, and that image is A dash B dash. This image falls between focus and 2f. As you can see in the ray diagram, this image is shorter than object. So the characteristics of the image will be position between f and 2f, size shorter than object, nature real and inverted. Third position is at 2f. Now the object is at 2f, as you can see. Now just see, if the object is at 2f, then one ray goes parallel to the principal axis, passes through the focus and falls on an image. Other ray passes to the optical center and cut the previous ray at 2f only. So we are going to have an image at 2f. This time, as you can see in the ray diagram also, the image is as long as the object is. Means the height of the image and the height of the object is same. The image is inverted, the image is real, and its position is 2f. So in this case, characteristics will be position of the image at 2f, size of the image as is equal to size of the object, nature real and inverted. Next position of the object is between f and 2f. Now as you can see the object, it is between f and 2f. So one ray goes parallel to the principal axis, cut on the A dash, passes through the focus, and other ray through the optical center cut the previous ray as A dash. So now we get an image which is beyond 2f. The size of the image is greater than the size of the object, and the image is, as you can see, it is real and inverted. In this case, characteristics of the image will be position beyond 2f, nature of the image real and inverted, size of the image greater than the object. When the object is at focus, at f should be, it is written 2f, please make it correct, it is at focus. When the object is at focus, then what happens? A ray passes parallel to the principal axis, it goes through the focus, other ray passes to the optical center and it goes parallel to the previous ray. Now what happens in this case? The image is formed at infinity. The image is real, the image is inverted. So the characteristics of the image will be nature of the image real and inverted, position at infinity, size highly magnified. Now the next and the very important case, between f and optical center. This is the only case when a convex lens makes a virtual image. Now what happens? One ray passes to the principal, parallel to the principal focus, parallel to the principal axis, passes through the focus and goes to the other side of the lens. Other ray passes through the optical center and goes undeviated. Now what happens when we see these two refracted rays, as you are able to see, so these two refracted rays, they are diverging from each other. So what we do? We actually extend the rays behind the lens so to get an image. So this time this image is virtual. It is greater than the object and it is erected. Characteristics of the image will be position behind object, size of the image greater than the object, nature virtual and erected. So these are the 6 positions for the convex lens. You have studied in class 10th also. Now let us move ahead. Image formation by concave lens. Now in image formation by concave lens, see again the important rays which helps us to define, to make the image. The one first ray is parallel to the principal axis. When it goes parallel to the principal axis, falls on the lens, as you can see in the ray diagram, it diverges from the principal axis. It diverges such that when it extended behind the lens, it passes through the focus. Okay, this is the definition of the first principal focus. Now for second principal focus, when a ray comes along a line which goes through the focus, second focus, then what happens? When it falls on the lens, then it goes parallel to the principal axis. Third one is when a ray passes through the optical center, then as definition of the optical center, the ray passes undeviated. Now, image formation by concave lens. So we have only two positions. When the object is at infinity, rays come parallel to the principal axis, falls on the lens and diverges from each other. When we extend the rays behind the lens, we get an image at f1. This time the image is point sized, which is virtual. Second position is when the object is between infinity and the optical center of the lens, anywhere the object can be. Now what happens? A ray passes through the principal axis, passes parallel to the principal axis, falls on the lens, diverges from the principal axis in such a manner that when the refracted ray is extended behind the lens, it falls on the f1. Now other ray passes to the optical center. So what we are going to have? We are going to have an image, and that image is A dash B dash. This time, as you can see, the image what we have got is virtual, it is erected, and its position is between focus and the optical center. So characteristics of the image in this case will be position between O and F1, size of the image is diminished, and nature of the image is virtual and erected. So this is the image formation by concave lens. Now move to the next, and the next is thin lens formula. What is thin lens formula? You have studied in class 10th. You must have remembered also. The thin lens formula is given by 1 upon f is equal to 1 upon v minus 1 upon u. This is the formula you have studied, but probably you didn't have proved this formula. So let us prove this formula. This formula is proved in three cases. One, the real image formed by the convex lens. Other is the virtual image formed by the convex lens. Third is the image formed by a concave lens. But we are going to prove this for only one case. Rest two cases will be your homework. Now let us start. Try to understand the method. Don't learn, try to understand. So first of all, let us prove this. First of all, we are going to draw a convex lens, its principal axis. We have an optical center of the convex lens. We have f dash. F dash is your first principal focus, and f is your second principal focus. Okay. We have 2f dash, 2f, that is twice of focal length. Now we kept an object between 2f dash and f dash, means the object is kept between 2f and f. So just I have told you, its image will be magnified, its image will be beyond 2f, its image will be real and inverted. So let us make the ray diagram so that we can prove it. One ray parallel to the principal axis passes through the second focus and goes like this. Other ray through the optical center, it cuts the previous ray beyond 2f, so we get an image, and that image is A dash B dash. So this is what the ray diagram looks like. Now we define one more point here, and that point is point of incidence of the ray which is parallel to the principal axis, and that point we call as x. Okay, so this is the ray diagram, and with the help of this ray diagram we are going to prove the lens maker's formula. Let us define the distances first of all. So from figure, the object distance OA, it is written as minus u because we are moving leftward, which is opposite to the direction of incidence of light. The image distance is OA dash. As you can see, it is moving, we are moving right side to measure the image distance. That's why it is taken as positive. Focal length OF, it should be OF. OF is equal to small f, that is your focal length. Height of the object, that is your AB, which is also equal to OX, and it is written as h because it is above the principal axis, so it is positive. Height of the image AB is minus h dash because it is below the principal axis. That's why it is taken as negative. Now, as if you remember, we have proved the mirror formula also. So in the same manner, we are going to prove the lens formula. First of all, we are going to consider the triangles, and we are going to consider two triangles such that they are similar to each other. And by property of similarity, we are going to define an equation, we are going to derive an equation which relates height of the image to the height of the object. So let us take an equation. Let us take some triangle. Triangle A dash B dash O, if you can see this image, and with the optical center, and triangle ABO. These two triangles are similar to each other because image and object, they are making 90 degrees from the principal axis, and at optical center the angles are vertically opposite, so they are equal to each other. Two angles are equal, so we can say that these two triangles are similar to each other. So triangle A dash B dash O is similar to triangle ABO. So now what happens? The ratio of corresponding sides must be equal. So what we are going to take? We are going to take height upon base in both the triangles. So in triangle A dash B dash O, the height of the triangle is A dash B dash and base of the triangle is OA dash. So we should write A dash B dash upon OA dash. And now in triangle ABO, the height of the triangle is AB and base of the triangle is OA. So it is AB upon OA. Now a bit of transposition takes place. AB is transferred to left hand side, OA dash is transferred to right hand side. We are going to have A dash B dash upon AB, and which is equal to OA dash upon OA. Now putting the values of all, A dash B dash is minus H dash, AB is H, which is equal to OA dash is V upon OA is minus U. Minus and minus and will be cancelled out. So we are going to have H dash upon H is equal to V upon U. Let this be your equation number 1. I hope till here it is clear. Now we are going to take another triangles, and these two triangles will be A dash B dash F. If you can see, A dash B dash F, image with the focus, and other triangle is OXF. OXF in the lens as with the focus. Now again, height upon base we are going to take. These two triangles are similar to each other. I hope you are able to understand that dotted line makes 90 degree with the principal axis. Image is also making 90 degree with the principal axis. One pair of angles at F in both the triangles will be equal because the angles are vertically opposite. Now these two triangles are similar to each other, so we can take the ratio of corresponding sides equal to each other. So now we are going to take height upon base in both the triangles. So let us see in triangle A dash B dash F, A dash B dash upon A dash F, and in triangle OXF we are going to write OX upon OF, height upon base in both the triangles. Now again the transposition takes place. OX is transferred to this side, A dash F is transferred to that side. So we are going to have A dash B dash upon OX is equal to A dash F upon OF. Now we know the value of A dash B dash, it is minus H dash. OX is equal to H only. A dash F we don't have, but OF we have, it is equal to focal length. So now what happens? We define A dash F. A dash F, if you are able to see, A dash F is the distance between image and the focus. This A dash F. This A dash F can be written as, just see, OA dash from here till here minus OF, minus this side. So if from here till here, if you minus this very length, so what we are going to have? From F to A dash only. So in this we are going to have, in place of A dash F we can write OA dash minus OF. Now put the values. A dash B dash is minus H dash, OX is H, OA dash is our V minus F upon F. Now if we adjust the minus sign from the left hand side to the right hand side, we are going to have H dash upon H is equal to F minus V upon F. Let this be your equation number 2. Now in equation number 1 and equation number 2 we can see the left hand side is same and the right hand side is also, the right hand side should also be same. So from 1 and 2 we are going to have V upon U is equal to F minus V upon F. By cross multiplying we are going to have FV is equal to UF minus UV, or UF is transferred to this side, so we are going to have F in bracket V minus U is equal to minus UV. Now UV is transferred to left hand side, f is transferred to right hand side, we are going to have v minus u upon uv, which is equal to minus 1 upon f. Or if uv is distributed on v and u, so we are going to have 1 upon u minus 1 upon v is equal to minus 1 by f. By adjusting the negative sign, we get 1 upon v minus 1 upon u is equal to 1 upon f, which is the required formula which we wanted to prove. So in this manner, the thin lens formula is being proved. So you have to prove for it virtual image also. You have to prove it for the virtual image made by the concave lens also. One more thing I wanted to mention here, that equation number 1 h dash upon h. Please remember this equation. We are going to use this equation for that height of the image upon height of the object, which is equal to image distance upon object distance. Please remember this equation. We are going to use it in the next few moments. Now let us move ahead. The next topic we are going to study is linear magnification. What is linear magnification? So linear magnification is the produced by the lens is defined as the ratio of height of the image produced by the lens to the height of the object. Basically, it is the ratio. It gives us the comparison between the height of the image and height of the object. It is a standard definition, and which is defined by the ratio of height of the image to the height of the object. So basically it is denoted by m. So m is equal to height of the image upon height of the object, which is equal to h dash upon h. Just a moment before, I have told you, please remember the equation that h dash upon h is equal to v upon u. So m can also be written as v upon u. So we have a formula here, and that formula is m is equal to h dash upon h, which is equal to v upon u. So this is the magnification in terms of image distance and object distance. Moreover, magnification can also be calculated in terms of focal length and the object distance. How it will be? Let us see. See, 1 upon v is equal to 1 upon u. 1 upon v minus 1 upon u is equal to 1 upon f. That is your thin lens formula. Multiply the whole equation by u. You are going to have u upon v minus u upon u is equal to u upon f. So u upon v becomes 1 upon m, as we have written in the above formula. Minus u upon u becomes 1 is equal to u upon u. Now 1 upon m will be equal to u upon f plus 1. 1 upon m will be equal to, by taking LCM we can write u plus f upon f. Now reciprocal the above equation, we are going to have m is equal to f upon u plus f. So this is the formula for magnification in terms of focal length and the object distance. This very formula can also be calculated in terms of image distance and focal length. How it will be? Let us see. The thin lens formula is given by 1 upon v minus 1 upon u is equal to 1 upon f. Now this time multiply the whole equation by v. So v upon v will become 1 minus v upon u will become m, and v upon f will remain v upon f only. Now 1 is transferred to that side, means right hand side. So we are going to have m is equal to 1 minus v upon f. By taking LCM we can write m is equal to v minus f upon f. So this is the formula in terms of image distance and focal length. So how the formula is being calculated, if you see the pattern, then when we had to calculate the relation for magnification in terms of focal length and object distance, we multiplied the whole equation by u. But when we had to calculate the relation for magnification in terms of focal length and image distance, then we multiplied the whole equation by v. So from here you should remember that if you have to calculate for object distance, multiply by the object distance itself, that is a u. And if I have to calculate in terms of image distance, multiply the whole equation by image distance, that is your v. But suppose if you have to calculate in terms of v and u only, then you have written the above formula, and that formula is h dash upon h is equal to v upon u. So this is what the linear magnification is. Now let us move ahead. Now the next topic is power of a lens, which is going to be our last topic of the day. What is power? So power is basically the ability of the lens to converge or diverge. How much a lens is converging or how much a lens is diverging. Suppose a lens is there which converges a parallel ray at 10 cm, means its focal length is 10 cm, and another ray is there which focal length is 20 cm, so it converges a ray at 20 cm. So which lens has more converging power? Obviously the ray which converges the ray nearby the lens, that lens has the more converging power. So basically the power is inversely proportional to focal length. So in this manner it is defined also. Mathematically it is defined as the reciprocal of focal length of the lens. So f is equal to 1 upon f, that is in meter, is equal to 100 upon f in centimeter. If you put f in meters, it will be f in meters, but if you have to put f in centimeters, then you have to write 100 upon f, which is f is converted into centimeters, so it will be 100 upon f. The important thing is its unit is diopter and this unit is represented by d. Now one more thing I wanted to remind you, that lens maker's formula we have studied, it was very important, and the lens maker's formula is given by 1 upon f is equal to mu 2 1 minus 1 upon r1 minus 1 upon r2. Now 1 upon f is equal to p also, so we can write p is equal to 1 upon f is equal to mu 2 1 minus 1 upon r1 minus 1 upon r2. So for power we have a formula, and that formula is written there. You should remember the formula. So this is all for today. Now for your home assignment, first question is, prove the thin lens formula for convex lens when the image is formed by the lens is virtual. Prove the thin lens formula. Prove the thin lens formula for concave lens. Plot a graph showing the variation. Third question is, plot the graph showing the variation of power of a lens with a change in its focal length. Means you have to draw a graph which shows the power and its focal length of the lens. Fourth question is, write some uses from lens of your day-to-day life. And now the fifth question is, solve NCERT question number 9.7, 9.8. If you don't have NCERT, please download it from the website of CBSE. In the next video lecture, I'll put a link to download the NCERT part 2 from the CBSE. So this is all for today. I hope you are studying at your home. I hope you are safe. Thank you for today.